A perfect stone pyramid has stood for nearly 5,000 years. That is not an accident, it is a calculation. This is the hidden mathematics of monumentality, the precise geometry and secret ratios that allowed ancient builders to conceive indestructible designs. By the end of this journey, you will see the world's most enduring wonders not as mysterious ruins, but as masterfully solved equations in stone. How did cultures with no modern tools encode the very constants of the universe into their architecture? What forgotten science of shape and force kept their creations standing through centuries of earthquakes and storms? The answer lies in a forgotten language, a numerical blueprint for immortality that we are only now beginning to fully decipher. What does it take to build something meant to outlast civilization itself? Before a single stone was set, the vision began with a line drawn in the earth. This was more than a measurement, it was a meditation. Ancient master builders understood that to create a structure meant to defy time, it had to first align with the universe. They sought a foundational blueprint not in arbitrary numbers, but in the very patterns of creation itself. This is the realm of sacred geometry, a language where shape is law. They observed that the same elegant proportions that govern a sunflower's seed head, the spiral of a galaxy, and the branching of a tree also seemed to dictate stability, harmony, and they believed a connection to the divine. For them, mathematics was not cold calculation. It was the architecture of consciousness, the thought of God made visible. At the heart of this system was a number so pervasive it seems woven into the fabric of reality, approximately 1.618, known as the golden ratio or phi. It is a proportion where a line is divided, so the longer part compared to the shorter part is the same as the whole line compared to the longer part. This creates a relationship of infinite, self-similar harmony. We see it in the perfect chambers of a Nautilus shell, each new segment growing by this exact ratio, and we see it meticulously reproduced in the columns of the Parthenon, its rectangular facade fitting perfectly within a golden rectangle. But why would builders care about a seashell? Because they saw in this ratio a universal principle of efficient, resilient growth, a natural blueprint for strength. This same principle manifests in the Fibonacci sequence, where each number is the sum of the two before it, 0, 1, 1, 2, 3, 5, 8, and so on. As the sequence grows, the ratio between successive numbers gets closer and closer to phi. This is the mathematics of organic progression, found in pine cones and flower petals, and it became a template for dynamic, living architecture. Beyond specific numbers, individual shapes held profound meaning. The circle, with no beginning and no end, symbolized unity, the heavens, and divine perfection. The square, with its 4 equal sides, represented the solidity of the earth, material stability, and the 4 cardinal directions. The triangle, especially pointing upward, signified aspiration, the journey from the earthly to the celestial, the very shape of a mountain or a pyramid. The pentagon, with its embedded 5-pointed star, was often associated with life and the microcosm. These were not just symbols, they were considered active components. A building grounded in the square and aspiring through the triangle was, in a sense, performing a ritual in stone, aligning itself with cosmic forces. The most staggering evidence of this encoded knowledge may be in the Great Pyramid of Giza. Its base perimeter, when divided by twice its original height, yields a number startlingly close to pi, 3.1416, the constant that defines a circle. This suggests the pyramid's design incorporates the squaring of the circle, a geometric puzzle representing the union of earthly and celestial realms. Furthermore, the pyramid's slope, angles, and dimensions are theorized by some researchers to encode astronomical relationships, and even the Earth's dimensions. This raises a profound question. Were these monuments merely tombs, or were they three-dimensional textbooks, stone repositories of a sophisticated science of form that we have only recently begun to rediscover with our computers? If the blueprint was this advanced, what tools could possibly have executed it with such impossible precision? The desert sun could not erase the lines they drew. With nothing more than a length of rope and a bag of wooden pegs, a team of surveyors began the most audacious construction project in human history. This is the first great paradox of monumental building. How did primitive tools yield perfect results? The answer lies in a profound understanding of geometry, where the chord itself became a living calculator. The most famous example is the Egyptian triangle, a simple but infallible method for creating a perfect right angle. By taking a rope knotted into 12 equal segments and forming a triangle with sides of 3, 4, and 5 units, they could instantly generate a 90-degree corner. This 3-4-5 triangle is a mathematical certainty, a built-in proof of the Pythagorean theorem centuries before Pythagoras was born. With this tool, they could lay out the perfectly square base of a pyramid, kilometer-long temple walls, or the foundations of a city, all with an accuracy that still baffles modern engineers. But a square foundation is useless if it is not level and perfectly oriented. Here, their ingenuity soared. To achieve a level plane across vast distances, they dug a grid of shallow trenches, filled them with water, and used the unwavering surface of the water as a giant reference line, chiseling the stone down until it just kissed the liquid plane. For cardinal alignment, turning the entire structure to face true north, south, east, and west, they turned to the night sky. They used an instrument called a merkit, a simple sighting tool made from a palm rib with a notch aligned with a plumb bob. By tracking the transit of specific, unchanging stars like Polaris or other circumpolar stars, they could fix meridian lines with astonishing precision. The Great Pyramid of Giza is aligned to the cardinal points with an error of just a fraction of a degree, a feat that would challenge modern surveyors with laser theodolites. This was not guesswork, it was a rigorous, repeatable celestial science. We see this same sophisticated application of simple tools far beyond Egypt. Consider the builders of Stonehenge. Thousands of years earlier, and with only wooden stakes and ropes, they orchestrated the placement of massive sarsen stones to align with the summer solstice sunrise. The heel stone, standing ominously outside the circle, casts its long shadow directly into the heart of the monument on the longest day of the year. This required not just observing the sun's path, but translating that observation into a permanent, monumental alignment on the ground, using geometry every bit as potent as the Egyptian triangle. So how could a rope and a bag of stakes achieve what our machines do today? The tool was not the source of the precision, the human mind was. The chord was merely the physical expression of an immutable mathematical law. The master builders did not see a knotted rope, they saw the manifestation of the 3-4-5 triangle. They did not see a trench of water, they saw the universal constant of a level plane. They did not just gaze at stars, they saw fixed points in an infinite celestial clockwork. The technology was basic, but the conceptual framework was extraordinarily advanced. This reveals the true foundation of these indestructible designs, a seamless marriage of elegant mathematics and flawless, disciplined execution. If the chord and the rule built the body of these monuments, what mind conceived their immortal soul? The blueprint was complete, yet the work could not begin. For the master builder, the moment of groundbreaking was not a logistical decision, but a celestial one. He was an architect priest, a singular figure for whom the slide rule and the star chart were one and the same instrument. In the highlands of the Maya, a daykeeper would retreat into a dark observatory, his eyes fixed on the brilliant wanderer we call Venus. He tracked its precise 584-day cycle, a rhythm as reliable as a heartbeat. Only when this morning star reached a specific alignment with other planets would he declare the auspicious day to lay the first stone for a new temple pyramid. This was not superstition, it was a profound belief that a building, to be truly eternal, must be born in harmony with the cosmos. Construction was a ritual act of world building, a literal reenactment of creation. Egyptian texts speak of the foundation ceremony as mimicking the moment the primordial mound rose from the waters of chaos. The architect priest, reciting from sacred scrolls, was not just building a structure, he was stabilizing the universe itself. This role required a mind that could hold multiple disciplines in perfect balance. We can think of it as a triad of expertise. First was the astronomer priest, the reader of the skies. He determined the sacred alignments, the solstice sunrise points, the passage of constellations that would dictate a building's orientation. Second was the master mason, the practical genius who understood the language of stone, stress, and load. He translated celestial angles into physical slopes and joints. Third was the scribe mathematician, the keeper of the sacred numbers and ratios. He ensured every dimension, from the grand plan to the smallest decorative element, adhered to the divine proportions of Phi or the symbolic numbers of their cosmology. These were not separate jobs, but often embodied in one extraordinary individual. The city of Teotihuacan, the place where gods were born, stands as a monumental testament to this fusion. Its vast avenue of the dead, flanked by the Pyramid of the Sun and the Pyramid of the Moon, is not a random arrangement. Researchers have found that the distances between these major structures mirror the proportions of our solar system. The relative spacing between the pyramids corresponds with striking accuracy to the distances between the orbits of the inner planets. Whether this is a conscious encoding or a miraculous coincidence, it reveals a mindset that saw the earthly city as a direct reflection of celestial order. Perhaps the most comprehensive example of this synthesis is Angkor Wat in Cambodia. This vast temple complex is a scale model of the Hindu cosmos. Its central towers represent the mythical Mount Meru, the axis of the world. The surrounding walls symbolize the mountain ranges at the edge of the universe, and the immense moat depicts the cosmic ocean, but the encoding goes deeper than symbolism. The entire layout is a precise astronomical observatory. On the morning of the spring equinox, an observer standing at the western gateway can watch the sun rise directly over the central tower, a dramatic alignment built into the very fabric of the design. Furthermore, the dimensions of the temple and the narrative bas-reliefs along its galleries are thought to encode the great cycles of time in Hindu cosmology, including the duration of planetary ages. This was architecture as a machine for understanding time, space, and divinity. So did these builders see their work as a permanent anchor for cosmic energy? The evidence carved in stone across the globe suggests they did. For them, mathematics was the language the universe was written in, and by speaking that language through their monuments, they sought to create a permanent, stable point of connection between humanity and the eternal. To translate such a grand cosmic vision into buildable reality required more than just philosophy. It demanded a practical, repeatable system. This is where their genius turned to a concept so simple and powerful it underpins modern manufacturing, the principle of modular design. A single, sacred measurement became the heartbeat of the entire project. This is the principle of modular design, the secret to building the colossal with flawless consistency. Imagine a master architect facing a mountain of stone and a workforce of thousands. His greatest challenge was not moving the blocks, but ensuring every single one, carved by different hands across many years, would fit together perfectly in the final vision. The solution was breathtakingly simple: establish one perfect unit of measure and let it govern everything. This unit was never arbitrary. The ancient Egyptian royal cubit, approximately 52.5 centimeters, was not just a length of wood or stone. Researchers like the archaeologist Jean-Philippe Lauer proposed it was a fraction of the Earth's polar radius, a tiny piece of the planet itself made portable. Whether this specific derivation is precise, the intent is clear. The builder's rule was meant to be a microcosm of cosmic order. This module did far more than measure, it orchestrated. First, it guaranteed proportionality. By designing the entire structure in multiples of the cubit, the relationships between height, width, chambers, and passages remained in perfect harmonic balance, no matter how vast the scale. Second, it enabled a kind of ancient mass production. Quarry workers used cubit rods to rough out identical blocks. Masons at the site used identical cubit templates to finish them. This turned chaos into a predictable, repeatable process. Third, and most brilliantly, it allowed for decentralized collaboration. A foreman at a distant quarry, a sculptor at the temple wall, and the chief architect at the drafting table all spoke the same numerical language. They did not need constant supervision, only the shared standard of the module. We see this genius system echoed globally. The Romans built their empire with the pes, or Roman foot. The Maya used the hanab. The builders of the Indus Valley civilization employed a unit called the danis. Each was a cultural signature, a repeating note in a symphony of stone. Nowhere is the power of the module more visible than on the Giza Plateau. The Great Pyramid's base side is famously 360 cubits. Its height was 280. But the modular thinking did not stop at the pyramid's edge. The dimensions of the Sphinx, the distances between the pyramids, and even the layout of the workers' barracks and bakeries all exhibit relationships based on the cubit. The entire complex was a single, integrated mathematical composition. This raises a fascinating duality. Was modularity merely a brilliant practical tool, or was it a philosophical statement? The answer is likely both. On one hand, it was the ultimate management tool, the key to logistical miracles. On the other, it reflected a deep belief in a universe built from orderly, repeating patterns, from the cells of a leaf to the orbits of planets. To build with a module was to participate in that universal order, to make human creation a reflection of natural law. But a perfect module and a celestial alignment are only the beginning of the story. The true test of a monument's immortality comes not from its plan, but from its battle with the relentless forces of nature. How do you make a structure of such immense weight not just stand, but stand forever? The spiral of a galaxy and the curve of a ram's horn share a silent, mathematical language. Ancient builders, gazing at seashells and the heavens, recognized these patterns as fundamental to a stable and beautiful universe. They sought to capture this perfection in stone, encoding the very constants of creation into their most sacred monuments. While they did not write the symbols pi or phi, their architecture demonstrates a profound, practical understanding of the relationships these numbers define. The Greek historian Herodotus recorded a tradition that the Great Pyramid's height was in such proportion to its perimeter that the area of each face equaled the area of a square whose side was the pyramid's height. This elegant description, when worked through, produces a ratio startlingly close to pi, approximately 3.1416. This was achieved through the pyramid's specific slope angle. If you take half the base perimeter and divide it by the height, you get pi. This suggests the builders intentionally designed the pyramid to embody the principle of the circle, the squaring of the circle made manifest in limestone. But the encoding goes deeper. The internal layout of the king's chamber forms a perfect 2 by 1 rectangle. The diagonal of this chamber's end wall, when extended, creates a relationship with the chamber's length that approximates the golden ratio phi. This same proportion is found in the pyramid's exterior dimensions, where the ratio of the apothem, the line from the apex to the midpoint of a base side, to half the base length, also approaches phi. This is not a single coincidence, it is a layered, intentional design. We see this mastery of constants applied differently across cultures. the Romans, masters of the arch and dome, showcased Pi in the pantheon. Its perfect hemispherical dome sits atop a cylindrical drum of equal height and diameter, a three-dimensional poem to the geometry of the sphere. The relationship between the dome's circumference and its diameter is, of course, pi. Meanwhile, in classical Greece, Phi governed beauty in the rectangular plane. The facade of the Parthenon fits almost perfectly within a golden rectangle. If you draw a rectangle around its frontal elevation, the ratio of its width to its height is 1.618. This proportion repeats in the spacing of its columns and the dimensions of its pediment, creating that timeless sense of harmonic balance we perceive as ideal beauty. A stunning synthesis of these principles exists at the Sun Temple in Connaught, India. This colossal temple, shaped like a divine chariot, is a masterpiece of encoded mathematics. The entire sculptural program, the spacing of its wheels, the proportions of its towering sanctuary, all are governed by the golden ratio. Every element, from the grandest tower to the smallest carved figure, relates to the others through phi, making the entire structure a single, unified expression of this cosmic proportion. Why would cultures separated by oceans and millennia obsess over these same irrational numbers? Pi and Phi are infinite, never repeating, never ending. They represent an unattainable perfection, a divine asymptote that human creation could forever approach but never quite reach. By embedding these constants into their monuments, the builders were not just constructing buildings, they were forging a permanent connection to the eternal and the infinite. Their work became a fixed point in the material world that resonated with the very fabric of the universe. Yet, to hold these perfect proportions aloft for centuries, the stone itself had to speak a different, more brutal dialect of mathematics, the relentless calculus of weight and force. The stone must hold its own weight, but also the weight of our gaze. This is the third strategy, a masterful deception in plain sight called Entasis. Look up at a towering Greek column like those of the Parthenon, and your eye tells you it is a perfect, straight cylinder from base to top. It is not. Each column possesses a subtle, calculated outward swell, a gentle curve that is the architectural equivalent of a whisper correcting a shout. Entasis is the deliberate bending of a straight line to make it appear straighter, and in doing so, making it structurally more resilient. It is a mathematical solution to a biological problem, human perception. The Roman architect Vitruvius explained it clearly 2,000 years ago. He noted that if you build a column with perfectly parallel sides, an optical illusion occurs when viewed from a distance. The middle will appear to sag inward as if buckling under the load. To correct this visual hollowness, the builders added a slight convex curve, restoring the impression of robust, unwavering strength. But this was far more than a cosmetic trick. The curve they applied was not arbitrary. It was typically a parabolic or elliptical curve, meticulously plotted. The process began with establishing the diminution, the rate at which the column would taper from its widest point, usually about 1/3 of the way up toward a narrower top. Then, using geometric rules, they would plot the gentle outward deviation from a straight line, a deviation that might only amount to a few centimeters over a 10-meter height. This subtle bulge did something remarkable to the physics of the structure. It created a more efficient path for the immense weight of the entablature above to travel down to the base. By slightly redirecting the lines of force, Entasis helped reduce shear stress, that dangerous sideways pressure at the column's foot, distributing the load more evenly through the stone's crystalline structure. The Parthenon is the ultimate textbook on this practice. Research has shown that each of its 46 outer columns has a uniquely calculated Entasis. They are not identical. The curvature was adjusted based on the column's position and the expected sightlines from key approach paths on the Acropolis. The corner columns, viewed against the sky, have a more pronounced curve to combat the stronger backlighting that would exaggerate the sagging illusion. This was architecture in dialogue with its environment and its viewer, a custom fit for both eye and earth. So was Entasis merely about aesthetics, a sculptor's vanity. The enduring silence of these stones suggests otherwise. It represents a profound, almost empathetic understanding that a structure's truth is not just in its measurable dimensions, but in how it is perceived and how it performs under strain. It acknowledges that to be truly strong, a design must account for the frailties of human vision and the hidden stresses within the material itself. This clever manipulation of vertical form was a prelude to an even greater defiance of gravity, one that required bending stone not outward, but into a soaring, weightless curve. The arch was waiting in the wings, a revolution in stone that turned compression into a superpower. Gravity itself was given a new shape to follow. The arch is not just a beautiful curve, it is a geometric rebellion against collapse, a way to make stone fly. Its principle is deceptively simple. It converts crushing vertical weight into a graceful outward thrust, channeling force along its curved limbs down to the ground. The engineer David P. Billington described it as a structure that lives by compression alone. Each wedge-shaped stone, called a voussoir, presses against its neighbors, locking them all in place. The central keystone at the apex is the final piece of the puzzle, the key that completes the self-supporting system. The secret of a perfect arch lies in its invisible geometry, the line of thrust. Imagine a chain hanging loosely between 2 points. It naturally forms a curve called a catenary. If you flip that chain upside down, you have the ideal shape for a pure compression arch, a curve where every stone carries only its share of the load straight down the line. Builders intuitively sought this shape, creating round Roman arches, the soaring pointed arches of Gothic cathedrals which directed weight more efficiently downward, and later, the parabolic arches that define modern engineering. The Pont du Gard aqueduct in France is a symphony in stone arches. This 3-tiered bridge, carrying water for a Roman city, has withstood 2,000 years of river floods and seismic tremors. Its endurance comes from repetition, each arch distributing its load to the next, creating a resilient, flexible whole that bends but will not break. To cover a wider space, the arch was extended into the third dimension, creating the vault, a ceiling of stone. The immense baths of Caracalla in Rome used vast networks of barrel vaults and groin vaults to create soaring, column-free halls for thousands of citizens. But how did a master mason know the precise angle to cut each wedge of stone? This was the culmination of their modular, geometric knowledge. Using full-scale templates drawn on a tracing floor, they could plot the exact shape and size of every single voussoir before a single block was quarried. The arch was the ultimate expression of a mathematical truth turned into structural poetry. Yet, this principle of compression held one final, majestic form in reserve, a shape that would enclose the heavens themselves. A dome is an arch spun on its axis, a perfect hemisphere of calculated equilibrium. To stand beneath the vast canopy of the Hagia Sophia or the Pantheon is to feel a profound spatial paradox, a ceiling of immense weight that appears to float, unsupported, over an ocean of empty space. This was the ultimate architectural ambition, to roof the heavens with stone. The Byzantine mathematicians Isidore of Miletus and Anthemius of Tralles, tasked with rebuilding the Hagia Sophia after a collapse, approached the dome not as artisans but as geometers. They understood that a dome is a continuous series of compressive arches all sharing a common keystone at the top. Each meridian, each line running from the base to the summit, acts like an arch channeling weight downward. But a dome introduces a new, dangerous force, hoop stress. As the weight pushes down the curved sides, it also creates a powerful outward push, like a barrel straining to burst its bands. The entire structure wants to pancake outwards. The solution was a breathtaking feat of engineering foresight. First, they built the dome not as a single, solid mass of heavy stone, but as a graded structure. At the base, where the compressive forces were greatest, they used dense, strong brick and mortar. As the dome rose, they switched to progressively lighter materials like porous clay bricks and even hollow ceramic tubes, reducing the deadly load at the top where the curvature is steepest. Second, and most crucially, they imprisoned the dome within a compressive ring. At the Hagia Sophia, this took the form of massive external buttresses and a continuous stone cornice at the dome's base, a belt of stone that cinched the outward thrust and redirected it down into the supporting piers. This was architecture as a permanent state of balanced tension. Different cultures solved the dome equation in distinct ways. The earliest method was corbelling, seen in the Mycenaean tholos tombs. Here, each successive ring of stones was laid slightly inward over the one below, like a stone honeycomb, until the opening could be capped with a single slab. It was a dome built by staircase, strong but limited in span. The Byzantine breakthrough was the pendentive, the elegant, curved triangular segments that allowed a round dome to sit gracefully upon a square base, magically transforming the geometry of the support. And in the Gothic world, the ribbed dome, like that of the Florence Cathedral, used a skeleton of stone ribs to channel weight precisely to specific points, allowing for a lighter, more daring shell between them. Yet, for sheer audacity of scale, nothing surpasses the Pantheon in Rome. Its unreinforced concrete dome, spanning 43 meters, has remained the world's largest for over 1,700 years. Its secret was a perfect hemispherical geometry combined with a masterful understanding of material science. The Roman builders used graded aggregate, mixing heavy travertine stone into the concrete at the thick base, then shifting to lighter volcanic tufa, and finally porous pumice at the very top. They even carved the famous coffered squares into the ceiling, not merely for beauty, but to remove excess weight without sacrificing strength. And at the very apex, the oculus, the open eye to the sky, served a structural purpose, eliminating the need for an unstable keystone at the dome's most critical point. What secret allowed such a relatively thin shell to span so wide? It was the precise, intuitive calculation of material properties, a proto-science of mechanics. The dome was not just built, it was grown, with its density and strength perfectly matched to the distribution of forces within its perfect curve. After conquering the sky with domes, the builders' ambition turned inward to a final frontier, the very ground beneath their feet. The stone had to be as perfect as the plan that shaped it. In the silent predawn of a quarry, a master would walk among the raw blocks, his hammer tapping each surface in a slow, deliberate rhythm. He was listening not for a dull thud, but for a clear, bell-like ring that sang of flawless, uncracked stone. This was the first equation in a monumental material science, a sensory test for hidden flaws. Ancient builders understood that geometry alone could not guarantee eternity. The very substance of their vision had to be chosen and shaped by its own hidden mathematics. They possessed an intuitive, profound grasp of what we now call anisotropic properties, the idea that stone has a grain, a directionality to its strength, much like wood. A granite block, for instance, is far stronger under compression when the force is applied parallel to its crystalline grain than across it. This was not written in a textbook. It was learned through generations of catastrophic failures and triumphant successes, a vast, unspoken database of empirical knowledge. To test a stone's compressive strength, they likely used methods of escalating pressure, perhaps loading a sample block until it fractured, observing the failure pattern to understand its limits. The Roman naturalist Pliny the Elder wrote of their revolutionary concrete, opus cementitium, with awe, noting its recipe could create structures to endure for eternity. This was no exaggeration. Their genius was in the mix, a combination of lime, water, aggregate, and a secret ingredient, pozzolana ash from volcanic regions. This ash contained silica and alumina, which reacted chemically with the lime and water to form a crystalline binder that not only cured rock hard, but could do so even underwater, making harbor walls and bridge piers possible. It was a material that grew stronger with time, a literal petrification process. Across the ocean, the Inca stonemasons of Sacsayhuaman in Peru demonstrated a different kind of material mastery. They worked with andesite, a notoriously hard volcanic stone. Through a patient, calculated process of pecking with harder stones and grinding with sand, they shaped massive blocks into polygonal puzzles. Each face was angled and curved with such precision that when set together, the joints disappeared, locking the wall into a monolithic, earthquake-resistant mass. The famous test is that not a single blade of grass, nor even a thin piece of paper, can slip between these stones. This was geometry applied at a microscopic level, a perfect mating of surfaces that distributed seismic shock evenly across the entire structure. Their material choices were a calculated index. They used granite for towering obelisks, valuing its immense compressive strength to stand tall and slender without fracturing. Sandstone, with its uniform grain, was chosen for detailed narrative carvings that would weather gracefully. Every mortar recipe, from the gypsum-based plaster of Egypt to the complex shell-lime mixes of Mesoamerica, was a chemical formula optimized for local climate and load. So did they have a numerical index for stone hardness? In a sense, they did. Their index was built from experience, passed from master to apprentice, a living data science that categorized materials by their performance under the hammer, the chisel, and the weight of centuries. This deep material intimacy was the final piece of the puzzle, but it presented a new, staggering challenge. How do you move a mountain of such perfectly chosen stone? The foreman's chant was the first equation of motion. With a rhythm as steady as a heartbeat, he synchronized the pull of 200 men, their muscles straining against ropes thick as a man's arm. Before them, a 200-ton statue of a pharaoh rested on a massive wooden sledge, a mountain of granite waiting to be walked across the desert. This was megalithic logistics, a living mathematics of mass movement where human coordination became a precise, calculable force. The master builders did not have cranes or engines, but they possessed an intimate understanding of physics, transformed into simple, scalable tools. Their first and greatest tool was the ramp, a temporary mountain of earth and rubble. Experimental archaeology, like the work of Mark Lehner at Giza, has demonstrated that the most efficient slope for dragging such immense weights is remarkably shallow, between 7 and 10 degrees. At this gentle incline, the force required to move a block is minimized. We can calculate this. The force needed is essentially the weight of the block multiplied by the coefficient of friction between the sledge and the ramp surface. By pouring water ahead of the sledge onto the desert clay or using a slurry of wet sand, they could reduce that friction dramatically, effectively creating a slick, artificial mudslide. On a 10-degree slope lubricated this way, moving a 200-ton block might require a pulling force equivalent to only about 10% of its weight. That is still 20 tons of force, a task for a small army. This is where the chant and the coordination came in. Teams would be arranged in precise rows along parallel ropes, their pulls synchronized to prevent jerking or twisting. The foreman's calls turned a chaotic crowd into a single, powerful machine. Beyond the straight ramp, evidence suggests the use of spiraling ramps that wrapped around a rising structure like a pyramid, allowing for continuous delivery of blocks to higher levels while using the same foundational footprint. But ramps were only one part of the equation. For finer placement and vertical lifting, the lever and fulcrum reigned supreme. A strong timber placed under a stone's edge with a smaller rock as a pivot point could use mechanical advantage to nudge a colossal weight incrementally upward or sideways. Teams would work in cycles, levering the stone up, sliding a wooden crib or stone pack underneath to hold the gain, resetting the lever, and repeating. It was a process of patient, ratcheted ascent. For the most bewildering feats of transport, we must look across the Atlantic to the Olmec of ancient Mesoamerica. Their colossal stone heads, each weighing up to 40 tons, were carved from basalt quarried in the Tuxtla Mountains. The astonishing fact is that these monoliths were then transported over 60 miles through swampy jungle and across rivers, all without the wheel, without metal tools, and without draft animals. The logistical planning this required is staggering. Researchers suggest they likely used a combination of log rollers and sledges, moving the heads along prepared causeways. They would have needed an acute understanding of terrain, choosing the firmest paths, and perhaps even constructing temporary roadways of packed earth and logs. Most critically, they mastered the distribution of weight. By balancing the head perfectly on its sledge and using a large team to pull on multiple ropes, they could navigate surprisingly complex landscapes. This was project management on a grand scale, directed not by software but by an astronomical clock. Work seasons were dictated by the Nile flood in Egypt or the dry season in Mesoamerica, when the ground was firm and labor was available from farming communities. The master builder's blueprint was thus a living document, a dynamic calculation that balanced human strength, material friction, seasonal time, and celestial timing into a single, executable plan for moving mountains. A single beam of light can mark the turning of the world. On the dawn of the winter solstice, the shortest day of the year, a narrow shaft of sunlight pierces the long, dark passage of Newgrange Tomb in Ireland, traveling for over 60 feet to finally flood the central chamber with golden light. This event was not left to chance. It is a feat of celestial engineering 5,000 years old. These monuments were more than tombs or temples. They were terrestrial clocks, colossal observatories built to track the grand cycles of the cosmos with breathtaking mathematical precision. Aligning a stone corridor to capture a specific sunrise requires solving a complex equation involving the Earth's axial tilt, the precise latitude of the site, and the slow precession of the seasons. The builders did not have telescopes or written formulas. They had patience and profound observational genius. Their primary tool was the horizon itself. By marking the rising and setting points of the sun against distant hills or notches over many years, they could pinpoint the solstices, the days when the sun appears to stand still at its northernmost or southernmost limit. For the more subtle equinoxes, when day and night are equal, they used gnomons, simple vertical poles. By tracking the length and direction of the pole's shadow throughout the year, they could identify the days when the shadow traced a perfect straight line from east to west. But some celestial cycles demanded generational memory. The moon's journey is even more complex, with a major standstill, a point where it rises at its most extreme northerly or southerly position on the horizon, occurring only once every 18.6 years. To encode this into architecture meant observing and recording for longer than a single lifetime, a testament to a culture dedicated to preserving cosmic knowledge in stone. The Maya of Mesoamerica left a stunning record of this dedication. The Dresden Codex, one of their surviving bark paper books, contains incredibly precise Venus tables. They track the planet's 584-day synodic period, predicting its appearances as the morning and evening star with accuracy that would not be matched in Europe for centuries. This was not abstract science, it was directly applied. The sacred timing for laying a temple's cornerstone or beginning a war was dictated by these celestial tables. Across the globe, we find this marriage of stone and sky. At the great temple complex of Karnak in Egypt, the main axis is aligned to the winter solstice sunset, so that on that pivotal day, the dying sun would shine directly down the columned hall into the sanctuary, symbolically rejuvenating the god within. High in the Andes, the Intihuatana stone at Machu Picchu, often called the hitching post of the sun, is a meticulously carved granite pillar. On the equinoxes, the sun casts no shadow at all from this stone, a perfect solar clock anchoring the Inca emperor's claim to divine connection. On the vast plains of Peru, the mysterious Nazca lines, giant geoglyphs etched into the desert floor, include long, arrow-straight pathways that point directly to the rising sun on the solstices and the setting points of important star clusters. Perhaps the most architecturally sophisticated example is the Caracol Observatory at Chichen Itza. This unique round tower, with its narrow slit windows, is precisely aligned to the extreme rising and setting points of Venus on the horizon. From within this stone instrument, a priest astronomer could watch the planet appear and disappear in these specific windows, marking the passage of time and the will of the gods with unerring accuracy. So were these alignments merely for ritual spectacle? The evidence suggests they served a far more foundational purpose. In a world without printed calendars or digital clocks, these monuments provided a perpetual, immutable framework for timekeeping. They dictated the agricultural cycle, when to plant and when to harvest. They regulated religious festivals and civic life. By tethering their society to the reliable, predictable motions of the heavens, the builders created a profound stability. The stone calendar would never break, the celestial clock would never need winding. This mirrored the very stability they sought in their physical structures, creating a world order that was both cosmically aligned and eternally resilient. Yet, even the most perfectly aligned stone is vulnerable to the Earth's own restless motion. The Earth's tremor is a language, and some ancient structures learn to speak it fluently. While a rigid modern building might fight a quake's energy until it shatters, a traditional Japanese pagoda is designed to dance, swaying with a graceful, calculated rhythm that dissipates the violent force. This is the sixth insight: seismic engineering as an intuitive mathematics of dynamic response, where flexibility trumps brute strength. At the heart of this ancient wisdom is a principle we now call base isolation, literally decoupling a building from the shaking ground. The master carpenters of Japan achieved this centuries ago through the Shinbashira, a central pillar that is the soul of a pagoda's resilience. This massive timber column is not firmly fixed at its base or top. Instead, it hangs loosely, suspended within the framework like a giant pendulum. When an earthquake strikes, the outer layers of the pagoda begin to sway in one direction. The heavy central pillar, due to inertia, lags behind, then swings back, acting as a counterweight that dampens the oscillation. It is a self-regulating system, a built-in shock absorber conceived long before the term was invented. This flexibility is amplified by the entire timber frame. Builders used intricate interlocking joints, assembled without a single nail. The famous Chinese dugong bracket system is a masterpiece of this approach, a complex network of wooden brackets that lock together under compression. During a quake, these joints can flex and groan, absorbing energy through friction as the wooden components rub against each other, rather than transmitting destructive forces through rigid connections. The heavy tile roof, which might seem a liability, actually serves a crucial purpose. Its immense mass gives the structure a low center of gravity and increases inertia, making the building more stable and its movements slower and more deliberate, like a deep sway rather than a brittle snap. We find similar intuitive physics across the seismic zones of the world. The Inca stonemasons, facing the volatile Andes, built walls with a pronounced inward taper. Each course of stone is set slightly back from the one below, creating a structure that is wider at the base and narrower at the top. This dramatically lowers the center of gravity, making the wall incredibly difficult to topple. In ancient Indian temple architecture, builders employed what are called fish belly girders, stone beams that are thicker in the middle and taper toward the ends. This shape perfectly mirrors the distribution of stress within the beam when under load, placing more material where the bending forces are greatest, a brilliant optimization of form following force. The 5-story pagoda at Horyuji Temple in Japan stands as the ultimate testament to this ancient science. Built in the 7th century, it has survived over 1,400 years of relentless earthquakes, including some of the most powerful in recorded history. It has never collapsed. Its endurance is no accident of fate. It is the result of a profound, embodied understanding of harmonic frequencies and resonant damping. The builders may not have had the equations, but they knew that a structure must have a natural frequency of sway different from the common frequencies of seismic waves in their region. By designing a tall, flexible tower with a heavy, suspended core, they ensured their pagoda would oscillate slowly and out of phase with the sharp jolts of the earth, allowing the energy to dissipate harmlessly. Their structures were not inert monoliths. They were complex, responsive systems engineered to absorb, redistribute, and ultimately dance with the energy of a restless planet. This deep harmony with natural forces extended beyond surviving disaster. It was woven into the very purpose of these places, aiming not just for stability, but for a specific, transformative effect on the human spirit. The most resilient shape in the universe has only 3 sides. Look at the skeleton of a modern bridge or the frame of a radio tower, and you will see a forest of triangles. This is no accident, it is a geometric law. A triangle is the only polygon that is inherently rigid. It cannot be deformed without changing the length of one of its sides. This principle, called triangulation, is the silent guardian of monumental design, a masterstroke of mathematical efficiency that ancient builders understood intuitively. The secret lies in how forces travel. When a load presses on a triangle, the stress is distributed evenly along its members, either in pure tension or pure compression. There is no weak point, no bending moment that can twist it out of shape without breaking it entirely. This makes it the fundamental unit of stable structure. The visionary architect Buckminster Fuller, who explored what he called tensegrity, the balance of tension and integrity in structures, was essentially working with a sophisticated network of triangulated forces. He was building on a principle as old as the hills. The most iconic application is, of course, the pyramid. A pyramid is not just a solid mass, it is a series of shrinking triangles stacked upon one another, a geometric funnel that channels the immense gravitational load of its own weight directly and efficiently down to the earth. Every stone is locked into this triangulated matrix, unable to shift without disrupting the entire perfect geometry. But the supremacy of the triangle extends far beyond the desert. Look at the majestic pediment of a Greek temple, that triangular gable crowning its facade. This was not merely a decorative space for sculpture, it was a critical structural element. The triangular shape transformed the downward weight of the roof and the horizontal thrust of the rafters into compressive forces that were safely channeled down into the columns below, preventing the walls from bowing outward. In the soaring Gothic cathedrals, the triangle became a dynamic, almost skeletal framework. The famous flying buttresses are essentially stone trusses, great arched triangles that leap from the outer walls to external piers. They catch the outward thrust of the vaulted ceiling and redirect it down and away from the delicate, glass-filled walls, allowing those walls to reach impossible heights. Even in the humblest dry stone walls, built without mortar, you will often find a zigzag or herringbone pattern. This crisscross arrangement creates a series of interlocking triangles within the wall's fabric, locking the stones together and distributing loads laterally, making the wall far more resistant to toppling than a simple stack of blocks. A fascinating case that speaks to material science alongside this geometric theme is the Iron Pillar of Delhi. This 7-meter-tall column of wrought iron has stood rust-free for over 16 centuries, a testament to an advanced metallurgical formula that created a protective passive layer. While the pillar itself is a cylinder, its enduring stability within the larger architectural complex of its time likely relied on the triangulated layouts of surrounding structures and platforms that anchored it against lateral forces. So why does this three-sided shape appear everywhere, from the molecular lattice of a crystal to the grandest spans of engineering? Because it represents the universe's most economical solution to a fundamental problem: how to create maximum strength with minimum material. It is the ultimate expression of calculated, efficient force, a geometric truth that builders have always known. If the triangle mastered the distribution of force, then the final frontier was not in the shape of the stone, but in the empty space it was meant to enclose. The temple's tower is not a single shape, but a cascade of them. As your eye climbs the soaring central spire of a South Indian gopuram, you see that its grand silhouette is not solid. It is composed of smaller, identical spires, each of which is adorned with even smaller niches and carvings that echo the same form again. This is not mere decoration, it is a profound mathematical signature written in stone, the seventh enigma: fractal complexity. A fractal is a pattern that repeats itself at different scales, a self-similar design where the whole contains miniature versions of itself, which contain even smaller versions, and so on toward infinity. It is the geometry of a snowflake, a fern leaf, a river delta, or a coastline, a pattern of organic growth and infinite complexity that creates forms which feel inherently alive and stable. Modern computer modeling reveals a stunning truth about fractal designs like the famous Mandelbrot set. They distribute physical stress with extraordinary efficiency. The branching pattern of a tree or a lung is a fractal because it is the most effective way to transport fluids or resist wind forces across a vast area with minimal material. Ancient builders, by observing the relentless patterns of the natural world, seem to intuit this principle of resilient form. They achieved this fractal effect through what we would now call a recursive algorithm in design, a simple rule repeated at ever smaller scales. The instruction might have been, take this shape and place a smaller version of it here, and then do it again. This is vividly seen in the honeycomb-like stalactite vaults of Islamic architecture, known as muqarnas. Each tiny cell-like niche is a miniature version of the larger vault, creating a breathtaking ceiling that seems to dissolve into infinite, crystalline complexity. At Chichen Itza, the Pyramid of El Castillo is a masterpiece of fractal scaling. The Great Pyramid is composed of 9 stepped platforms, but on each of its 4 stairways, the pattern of the steps creates a smaller, nested pyramid within the facade. The entire structure is a geometric echo of itself, yet the ultimate expression of this cosmic recursion is the Angkor Wat complex. The entire layout is a fractal model of the Hindu universe. The vast moat represents the cosmic ocean. The outer walls symbolize the mountain ranges at the edge of existence. The central towers embody Mount Meru, the axis of the world. But then you zoom in, and each enclosure within the complex repeats this pattern, with its own symbolic walls and central shrines. Zoom in further to a single tower, and its carved details and miniature pinnacles repeat the motif yet again. From the grandest plan to the tiniest bas-relief, the same pattern of order is maintained. This creates a visual and structural harmony that is deeply calming to the human mind, perhaps because it mirrors the very patterns of branching neurons in our own brains. Did these architects understand that by building fractals, they were tapping into nature's own blueprint for resilience? The evidence suggests they knew that a design which echoed the growth of a tree or the flow of a river would possess a timeless, organic stability. This recursive harmony leads our gaze from the grand shape down to the infinitesimal detail, and finally to the silent, potent spaces in between. The stone itself became the final, perfect joint. Run your hand over the seamless joinery of an Incan wall in Cusco, and you are not touching a construction, you are touching a 3-dimensional puzzle solved with impossible precision. This is Mortarless masonry, the pinnacle of stonecraft, where the bond is not a sticky paste but pure, calculated geometry. The 16th century Spanish chronicler Pedro Cieza de Leon wrote with awe that in these walls, not even a needle could fit between the stones. This was not a mystical art, but a supreme, tactile application of mathematics. Each granite or andesite block was a unique, multi-faceted shape, its every angle and curve calculated to interlock with the specific contours of its neighbors. The process was a masterclass in iterative fitting. First, a master mason would select a rough block and position it near its intended home. Using a harder stone as a hammer, he would begin pecking away, shaping one face to match the stone already in place. He would then use sand and water to grind the surface smooth, constantly testing the fit. This was not guesswork. It was a slow, deliberate dialogue between the mason, his material, and the growing wall. Some researchers suggest they may have used clay molds to take an impression of a gap, creating a precise template to guide the carving of the next stone. The result was a wall that behaved not as an assembly of pieces, but as a single, monolithic entity. This was the secret to its legendary earthquake resistance. During a tremor, a rigid, mortared wall cracks along its straight, weak joints, but a polygonal Incan wall with its complex, interlocking facets could flex and sway. The stones would shift minutely against one another, dissipating the seismic energy through friction, and then settle back into their original, perfect alignment once the shaking stopped. The wall was alive, a dynamic system. Stability was further enhanced by a subtle but intentional design. The walls were built with a slight inward tilt, lowering the center of gravity and making them incredibly difficult to topple. The most famous example is the 12-angled stone in Cusco, a masterpiece of calculated load distribution. This single block, with its 12 perfectly carved sides and corners, interlocks with its neighbors in a dizzying array of directions. Each angled face channels the weight and force from the stones above and around it along multiple vectors, spreading the stress across a wide area of the wall. It is a geometric anchor. So was this relentless pursuit of seamless joinery merely about structural efficiency, or was it something more? The Incas saw their empire, Tahuantinsuyu, as a perfectly ordered whole. Their architecture, from the grandest terrace to the smallest stone, reflected this ideal of unity. A wall without gaps was a symbol of an unbreakable society, a physical manifestation of harmony and strength. This level of precision required more than skill. It demanded a deep, almost intuitive understanding of three-dimensional space, a mind that could visualize complex polyhedra and how they would fit together under the immense pressure of a mountain city. It was geometry made tangible, a testament to the human capacity to shape not just stone, but the very forces of nature through patient, perfect calculation. The quiet inside a 5,000-year-old tomb feels different from any other silence. It is a dense, resonant stillness that many visitors describe as palpable, almost alive. This sensation lies at the heart of an ancient practice far more complex than simple superstition, geomancy, the art of reading the earth itself to find the perfect place to build. While wrapped in the language of dragon lines and terrestrial spirits, this eighth practice reveals a sophisticated, mathematical dialogue between builder and landscape. At its core, geomancy was about harnessing the unseen forces of a location, not through magic, but through meticulous observation of the land's hidden logic. The first calculation was always one of stability. A master geomancer would never place a temple on loose soil or in a river's floodplain. He sought bedrock, the unshakable foundation that would anchor a monument for millennia. This was a practical equation of load-bearing capacity, solved not with soil samples, but with generations of knowledge about which hills held firm and which slopes slid away with the rain. In China, the elaborate system of feng shui formalized this knowledge. Practitioners used the luopan, a complex compass inscribed with concentric rings of astrological and geographic data to determine the most auspicious orientation for a building. The goal was to align a structure with the so-called dragon lines or longmai, believed to be channels of vital energy flowing through the earth. Stripped of its metaphysical layer, this often meant aligning a building to catch the prevailing winds for ventilation, to avoid the path of seasonal mudslides, or to position it over a stable geological formation. They were, in effect, mapping beneficial microclimates and safe ground. This sensitivity extended to water, not just as a resource, but as a thermal regulator. There is evidence that some ancient builders could detect underground water channels through methods like dowsing. By building over these hidden streams, they may have unintentionally created a natural cooling system, as the constant movement of water deep below would subtly lower the ground temperature around the foundations, a passive form of climate control. The choice of a hilltop, so common for fortresses and temples, solved multiple equations at once: defensibility, drainage, visibility, and often proximity to the heavens. But perhaps the most mathematically intriguing aspect of geomancy involves sound and resonance. The hypogeum of Hal Saflieni in Malta, a labyrinthine underground sanctuary carved from solid limestone around 3200 BC, possesses extraordinary acoustic properties. Certain chambers are tuned to specific resonant frequencies, where a deep voice can create vibrations felt throughout the body. This was not an accident. The builders likely selected and shaped this particular site because the density and composition of the limestone here produced these unique sonic effects, turning the earth itself into a sacred instrument. Across Europe, many Gothic cathedrals were deliberately constructed atop older pagan sites, which were themselves often situated at geological crossroads, places where different rock strata met or where magnetic anomalies were detected. These locations, often described as having a special energy, might have offered practical advantages, stable foundations from the rock interface, or perhaps even subtle effects on the local climate or groundwater flow that made the site feel inherently different. So were the builders sensing a mathematical harmony between the Earth's hidden grid and their celestial alignments. The evidence suggests they were holistic engineers. They understood that a truly indestructible design could not fight its environment. It had to converse with it. By reading the landscape as a complex system of forces, slopes, materials, and energies, they ensured their structures were not just placed on the earth, but woven into its very fabric. This deep integration meant the monument became a permanent feature of the landscape, as natural and enduring as a mountain. Yet, even the most perfectly sited structure faces a final, relentless mathematician, the one that measures not in years but in millennia. Sandstone surrenders to the wind grain by grain while granite waits. This was the final, most patient equation the master builders had to solve, not just how to build, but how to build for a future they would never see. They were not merely constructing against gravity, but against time itself, modeling the slow mathematics of decay and choosing their designs as deliberate countermeasures. Every environment whispered a different threat. In deserts, the enemy was wind-driven sand, a relentless abrasive blast. In northern climates, it was the freeze-thaw cycle, where water seeps into microscopic pores, freezes, expands with incredible force, and shatters the stone from within. Along coastlines, the destroyer was salt crystallization, where evaporating seawater leaves behind crystals that grow and fracture the material like a slow explosion. The Roman architect Vitruvius wrote plainly that an architect must understand the nature of the climate, for buildings are to be made fit for use in one kind of site but unserviceable in another. This was not a suggestion, it was a foundational law of survival. Their response was to engineer solutions that functioned like mathematical proofs against these forces. Take the classic pyramid form. Its steep, smooth slope is not just a symbol of ascent, it is a highly efficient geometric defense. By minimizing the total surface area exposed to the prevailing wind at a perpendicular angle, the design drastically reduces the area vulnerable to sand abrasion. The wind simply glances off the angled face, carrying its abrasive load up and over the structure. It is a shape calculated for minimal friction with the atmosphere. But the builders went further, developing a toolkit of preservation strategies encoded into the architecture itself. They employed hard capping stones, dense, impervious slabs placed at the very top of walls and columns to shield the more vulnerable masonry below from direct rainfall and ice. They designed sacrificial layers like the outer casing stones of pyramids, meant to weather and be replaced, protecting the core structure. They formulated breathable mortars, mixes that allowed trapped moisture to evaporate out rather than being locked inside to freeze and destroy. A masterclass in this calculated material stratification is the Roman Colosseum. Its builders were not just stacking stone, they were composing a vertical defense system. At the ground level, where constant capillary moisture from the earth and the splash of crowds would cause the most damage, they used travertine, an incredibly dense limestone highly resistant to water. As the structure rose, they switched to lighter, more porous tufa for the upper levels, where the primary threats were weight and wind, not ground moisture. Each stone was placed according to a precise understanding of the environmental forces it would face at that specific height. This raises a profound question. Did these architects run millennia-long experiments in their minds? They had no accelerated weathering chambers, no computer simulations. Their laboratory was the landscape itself, observing which old walls still stood and which had crumbled, learning from the failures and successes of centuries. Their genius was to extrapolate those observations into a forward-looking calculus of preservation. They did not just build for their present, they built for a future they conceived of in terms of geological time. Their success is etched into the very stones that have refused to fall. So what can we, with all our technology, learn from them today? Perhaps it is this, that true sustainability is not a trendy add-on, but the very first line drawn in the sand, a deep conversation between design and the relentless, beautiful mathematics of a changing world. The blueprint was never a single scroll locked away in a vault. It lived in the rhythm of a chant, the precise angle of a master's hand guiding an apprentice's tool, and the measured steps of a ritual dance performed at the laying of a cornerstone. This is the ninth and perhaps most fragile legacy, the transmission of knowledge, a living mathematics passed from mind to mind and generation to generation without a single formal textbook. In a world before printing presses, how could the exacting ratio for a perfect column or the celestial alignment for a temple be preserved across centuries? The answer lies in a culture's collective memory, ingeniously encoded. Complex principles were transformed into memorable patterns. A master builder might teach the proportions of the golden ratio through a repetitive song, its verses embedding the sequence 1, 1, 2, 3, 5, 8 into the apprentice's memory as surely as notes on a staff. Ritual dances could physically enact geometric relationships, with the length of a step or the span of outstretched arms corresponding to sacred units of measure, turning the body itself into a calibrated instrument. For visual reference, simple but precise geometric drawings were scratched onto plaster walls at the construction site or inked onto precious papyrus. These were not full architectural plans as we know them, but symbolic keys, diagrams of essential relationships, the ad quadratum and ad triangulum methods that generated all proportions for a Gothic cathedral from a single square or triangle. The surviving sketchbook of the 13th century Mason Villard de Honnecourt is a priceless window into this world. Its pages are filled with coded diagrams of machinery, architectural details, and even figures, all annotated with cryptic notes meant for initiates who understood the lodge's secret language. This knowledge was guarded within mystery schools and guilds, with master numbers and core geometric secrets revealed only after years of apprenticeship and sworn oaths of secrecy. The methods of encoding this data were as diverse as the cultures themselves. In the Andes, the Inca used the quipu, a complex array of knotted strings where the position, color, and type of knot recorded numerical data, possibly even narrative information, turning a bundle of chords into a three-dimensional ledger of resources, lineages, and perhaps architectural formulas. Across Europe, notched tally sticks served as both legal contract and building record, the notches representing quantities of materials or work completed, a physical IOU and blueprint combined. And often, before the grand project began, a scale model was crafted, not a tiny decorative piece, but a functional, detailed guide made of wood, stone, or even clay, from which every dimension could be scaled up using the master module. This living library of knowledge, stored in chant, dance, diagram, and model, possessed a remarkable strength, adaptability. When cultures met through trade or conflict, these encoded principles could be exchanged, compared, and hybridized. A Byzantine master fleeing upheaval might bring the secret of a pendentive to a Western guild, where it was absorbed into their lodge traditions. This system ensured the knowledge was not static but evolving, tested and refined by each new generation of hands. So was the true, indestructible design finally just a set of numbers on a page. The enduring stones suggest otherwise. The most resilient blueprint of all was the one inscribed into the very culture, a shared understanding that lived in the practiced hand, the trained eye, and the communal memory, allowing humanity's grandest mathematical dreams to be rebuilt again and again from the ground up. A step pyramid rises from the desert, its silhouette a staircase to the sky. An identical form emerges from the jungles of Mesoamerica and another from the plains of Mesopotamia. These cultures were separated by vast oceans and thousands of years with no evidence of a shared blueprint. Yet they each arrived at the same monumental solution, a geometric echo across the globe. This is the phenomenon of cultural cross-pollination without contact, a profound hint that the mathematics of monumentality may be woven into the very fabric of human intuition. When faced with the same problem, how to build tall, stable, and sacred, different minds in distant lands calculated the same answer. The step pyramid or ziggurat is a triumph of basic, resilient geometry. A series of stacked, shrinking platforms creates a stable structure with a low center of gravity. Its broad base defying collapse, while its stepped sides provide a built-in ramp for construction and ritual ascent. It is a form that emerges almost inevitably from the logic of piling stone upon stone toward the heavens. The anthropologist Claude Lévi-Strauss spoke of universal structures of the mind, deep patterns of thought that shape how humans categorize and create. Could it be that certain geometric forms act as archetypes, pre-existing templates in our collective consciousness that are drawn upon when we seek to make meaning in stone? This psychology of form suggests an innate human attraction to shapes that embody stability, power, and connection. The circle, for instance, appears as a sacred ideal from the stone circles of Britain to the mandalas of Asia. It represents unity, cycles, and the celestial dome, a shape without weakness or beginning. The corbelled arch, where each stone course projects slightly inward until meeting at the top, was invented independently by Mycenaean tomb builders in Greece and Mayan architects in Central America. It is the logical, geometric solution for spanning a space with horizontal stone, a convergent innovation born from material constraints. Even the constant pi, the ratio of a circle's circumference to its diameter, was approximated in circular structures worldwide, from the great kivas of the ancestral Pueblones to the hemispheric domes of Rome. It was not a transmitted secret, but a relationship discovered by anyone who tried to build a perfect round form. the most striking parallel of all is cardinal orientation. The Great Pyramid of Giza is aligned to true north with minuscule error. Thousands of miles away and centuries later, the Pyramid of the Sun at Teotihuacan achieves a similarly precise alignment. They shared no known surveyors, no exchanged letters, but they did share the same night sky, the same rotating planet, and the same human desire to anchor their greatest work to the immutable directions of the cosmos. By observing the same circumpolar stars or the sun's solstice points, isolated cultures could independently derive the same cardinal axes. This convergence points not to a lost super-civilization, but to something perhaps more remarkable, a shared mathematical language born from humanity's universal dialogue with nature. We all observe the same forces of gravity, the same need for stability, the same awe at the cyclical heavens. When a culture reaches for monumentality, it reaches with the same human hand and the same human mind, working through the same physical and perceptual problems. The local expression varies: the limestone of Egypt, the volcanic rock of Mesoamerica, the mud brick of Mesopotamia, but the underlying geometric grammar reveals a common ancestry of thought. This suggests the indestructible design was not invented but discovered, a set of eternal principles waiting in the stone and the stars for any builder with the patience and vision to listen. A whisper can travel across a stone room and arrive unchanged. In the heart of the so-called treasury of Atreus, a massive Mycenaean tomb, you can stand at the entrance and hear the softest words spoken at the central chamber with startling clarity. This is not a quirk of construction, it is a calculated feature. This 10th revelation is acoustic engineering, the ancient mathematics of sacred sound, where architecture was designed not just for the eye, but for the ear. Builders treated sound as a tangible material to be shaped, focused, and amplified through precise geometry, adding an invisible, immersive layer of permanence to their stone visions. They understood intuitively what physics explains, that sound waves reflect off surfaces, combine in spaces, and can be made to resonate at specific frequencies determined by a room's dimensions. An elliptical chamber, for instance, creates a whispering gallery effect. Because of its unique shape, sound waves travel along the curved wall, reflecting in such a way that a person whispering at one focal point can be heard clearly at the opposite focal point, even across a vast distance. While the famous example is in St. Paul's Cathedral, the principle was discovered and exploited millennia earlier. At Chavin de Huanta in the Peruvian Andes, archaeologists uncovered a 3,000-year-old network of labyrinthine stone ducts. When conch shell trumpets were blown into these tubes, the sound would echo and distort, emerging as a terrifying, bestial roar from different parts of the temple complex. This was not for entertainment, it was a form of psychological and spiritual theater, using manipulated sound to create an aura of divine presence and awe. The builders achieved these effects through deliberate design choices. They carved niches that acted as Helmholtz resonators, cavities of a specific volume and neck size that would amplify a particular frequency when sound passed by, much like blowing across the top of a bottle produces a specific note. Corbelled stone domes, like those in early Irish passage tombs, were shaped to focus and project sound toward a specific point. Even material selection played a role, choosing highly polished limestone for bright, clear reflections, or using porous sandstone to subtly absorb certain tones and reduce reverberation. Perhaps the most intriguing acoustic case study lies within the Great Pyramid itself. The ascending passage leads to the Grand Gallery, a majestic, corbelled corridor over 150 feet long. Researchers have noted that the dimensions of this gallery, its length, height, and sloping angle, may have been calculated to resonate at very low infrasonic frequencies below the range of human hearing. While we cannot know the builder's intent, modern studies suggest exposure to such frequencies can produce feelings of unease, awe, or even altered states of consciousness. Was this a side effect, or was it the purpose? The evidence from global sites suggests sound was a core component of the sacred experience. To stand in these spaces was to be surrounded by the architecture, to feel its vibrations in your bones as much as see its form with your eyes. The mathematics of monumentality thus extended into the realm of the sensory and the psychological, using calculated form to shape not just space, but the very experience of being within it. This pursuit of total environmental control leads to a final, unifying question, one that looks beyond any single technique toward the ultimate purpose behind it all. 72 pillars held the sky above the temple of Karnak, a number that whispers of a deeper code. It is not merely a count, but a key, for it also marks the years required for the equinoxes to shift a single degree along the zodiac, a phenomenon known as the precession of the equinoxes. This is no coincidence, it is symbolic numerology in action, a layer of applied mathematics where numbers were not just quantities, but carriers of cosmic meaning. For the ancient mind, there was no division between the practical and the symbolic. A number could measure a wall and simultaneously embody a divine principle. The theologian St. Augustine captured this perfectly when he wrote that numbers are the thoughts of God. To build with a sacred number was to weave a thread of the universe's own logic into the fabric of a monument. This practice gave rise to a lexicon of potent numerals that dictated architectural plans across cultures. The number 7, representing the visible wandering planets, might govern the tiers of a ziggurat. 9, often symbolizing the cosmic layers or steps to heaven, defines the magnificent stepped terraces of Borobudur in Indonesia. 12, for the signs of the zodiac or the months of the year, appears in structures like the Tower of the Winds in Athens, with its 8 sundial faces and sculpted figures of the 8 winds, yet its interior design and broader symbolism often tie back to the 12-fold division of time and sky. Then there is 108, a number of profound completion in Hindu and Buddhist thought, derived from multiplying the sacred 12 by the cosmic 9. This number appears not only in prayer beads but in the very infrastructure of ancient cities, like the 108 granary pits found at Harappa in the Indus Valley. To understand how this symbolic layer coexisted with rigorous geometry, consider the Basilica of San Vitale in Ravenna. Its breathtaking central plan is not a circle or a square, but a perfect octagon. The number 8 in early Christian symbolism represented regeneration and rebirth, the new creation that began on the 8th day, the day of the resurrection. This was not an aesthetic whim. The octagonal form governed everything from the overall footprint to the proportions of the ambulatory and the placement of the columns and arches. The symbolic number provided the conceptual framework, and the practical geometry of the octagon provided the buildable, stable shape to express it. So did the builders believe that by embedding these numbers, they were instilling the structure with the power of the cosmos itself. The evidence inscribed in stone across the world suggests they did. They operated from a unified world view where mathematics was the connective tissue between the earthly and the celestial, the measurable and the mystical. A column count was both a structural necessity and a stellar hymn. This symbolic coding reveals the ultimate ambition of the master builders to create a monument that was not merely a physical shelter, but a resonant vessel, perfectly tuned to the hidden frequencies of a meaningful universe. A crack in the stone speaks a language of forgotten forces. While we marvel at the monuments that stand, the ones that fell or faltered hold an equally vital truth, a library of data written in fracture lines and leaning walls. This 11th analysis reveals failure not as an ending, but as a critical step in the ancient equation, the moment where theoretical mathematics met the unforgiving reality of physics. Each collapse was a brutal but essential experiment, refining the rules of indestructible design through hard, tangible feedback. Forensic engineering, when applied to ancient ruins, becomes a form of archaeological detective work, reading stress patterns like a story. The majestic Basilica of Maxentius in Rome, for instance, today shows us its colossal vaults lying in ruin. The pattern of its collapse points clearly to the immense lateral thrust generated by those wide arches, a force that eventually overcame the resisting strength of its walls. It is a permanent lesson in the balance between ambition and counterforce, a lesson later builders would take to heart with flying buttresses. We can categorize the common failure modes that challenged these master calculators. Foundation settlement was a primary threat where the ground itself proved an unreliable partner. The iconic Leaning Tower of Pisa is the world's most famous lesson in soil mechanics. Its gradual tilt caused by a foundation built on soft, compressible clay that could not uniformly support its immense weight. The builder's mathematical precision above ground was undone by the variable earth below. Another pervasive challenge was the lateral thrust from arches and vaults, the outward push that demands an answering resistance. Many early domes and barrel vaults collapsed because the walls built to contain that thrust were simply not thick or strong enough, a miscalculation of horizontal force. Then there was material fatigue, the slow, silent degradation from environmental stress, like the wind-driven erosion that has softened the body of the Great Sphinx over millennia, a reminder that even the most resilient stone has a conversation with time. Perhaps no single structure better embodies this process of live correction than the bent pyramid at Dosha in Egypt. Its unique profile, with a steep lower section that abruptly changes to a shallower angle near the top, is not a stylistic choice. It is widely believed to be a mid-construction correction. The initial, steeper slope likely began to show alarming signs of instability, perhaps excessive stress or even minor collapses in the internal chambers. The builders, in a stunning display of adaptive engineering, recalculated. They changed the angle for the upper portion to a gentler slope, redistributing the weight more safely. This architectural pivot was a monumental moment of learning, directly informing the perfectly angled, smooth-sided pyramids that followed, including the Great Pyramid at Giza. The repeated collapses of the Hagia Sophia's first Great Dome followed a similar pattern of iterative refinement. Each failure taught Isidore of Miletus and Anthemius of Tralles more about the dome's deadly hoop stress, leading to the final, triumphant design with its stronger supporting piers and graded, lighter materials. What mathematical lessons were carved into these ruins? They taught the precise relationship between height and base, the critical need for deep, stable foundations, and the non-negotiable requirement for counteracting thrust. Each failure was a boundary marker, defining the limits of the possible and pushing the next generation of builders to develop new solutions, new geometries, and new materials. The indestructible designs we admire today were not first attempts. They were the brilliant, hard-won answers to questions written in dust and rubble. The administrative feat of marshalling resources for 3 giant pyramids at Giza is almost beyond comprehension. This was not just big construction, it was the dawn of megaprojects governed by a ruthless, hidden calculus. When you decide to build the colossal, the challenges do not simply add up, they multiply in a non-linear explosion. This is the realm of scaling laws, where the mathematics of size itself becomes the primary architect. At the heart of this lies a principle known as the square-cube law, a simple geometric truth with monumental consequences. If you double the dimensions of a structure, its volume, and thus its weight, increases by a factor of 8, it cubes. However, the cross-sectional area of its supports, the pillars or walls holding it up, only increases by a factor of 4, it squares. This means the weight-bearing capacity of the supports grows much more slowly than the load they must carry. The engineer J.E. Gordon put it perfectly when he said an elephant cannot look like a scaled-up mouse. If you simply enlarged a mouse to elephant size, its legs would be far too thin relative to its new, immense weight, and they would snap. The elephant's legs are not just longer, they are proportionally much thicker, a complete redesign to meet the new scale. Ancient builders confronted this same law of physics intuitively. They understood that to build taller and heavier, they could not just repeat the same design on a bigger canvas. They had to reinvent the geometry of support. This meant designing much thicker walls at the base, creating internal compartmentalization with cross walls to distribute loads, and strategically using stronger, denser materials at the points of greatest stress. The evolution from the step pyramid of Djoser to the Great Pyramid of Khufu is a masterclass in this applied calculus. The step pyramid is a stack of mastobas with a relatively narrow base and steep sides. The Great Pyramid, however, represents a quantum leap in understanding mass distribution. Its vast, perfectly square base provides an enormous footprint to spread the unprecedented weight. Its smooth, angled sides form a continuous triangulated funnel, channeling gravitational forces directly into the bedrock. It is the architectural equivalent of evolving from a mouse to an elephant, a complete morphological shift to conquer scale. But the square-cube law was just one equation in a vast system. Scaling up triggered a cascade of other non-linear challenges. Logistics became exponentially harder. Moving a 200-ton granite block requires more than twice the effort of moving a 100-ton block. It demands a complete reorchestration of ramps, ropes, and manpower. Providing food and water for the workforce ballooned from feeding a village to sustaining a small city for decades, a feat of agricultural and hydraulic planning that rivaled the construction itself. And perhaps most critically, the management hierarchy had to transform. Direct oversight by a single master builder becomes impossible. The project required a decentralized command structure with foremen for quarries, ramps, masonry, and logistics, all communicating through the common language of the sacred qubit module. This was early bureaucratic mathematics, the geometry of human organization. So how did they know when they had reached the absolute limit of what was possible with their technology? Their greatest monuments stand precisely at that precipice. The Great Pyramid is the largest and most precise of its kind, a peak that was never surpassed in Egypt. Later pyramids are smaller, often less perfectly built. This suggests that Khufu's builders had calculated their ambition to the very edge of the feasible, harnessing every ounce of available knowledge, labor, and material to create something that balanced on the knife edge of physical possibility. They did not just build big, they solved the profound equation of the colossal, where every increase in scale demanded a revolutionary leap in understanding. A supercomputer hums, calculating the precise stress on every digital stone of a virtual coliseum. This is the 12th perspective, where our most advanced mathematics turns its gaze backward, not to replace ancient genius, but to finally understand its full vocabulary. Modern technology allows us to reverse engineer these monuments, conducting conversations with the past through lasers, particle physics, and vast computational power. We are no longer just observers, we are active participants in a scientific dialogue that decodes intentions hidden for millennia. The process begins with seeing the structure in impossible detail. Three-dimensional laser scanning, or LIDAR, bathes a monument in millions of precise laser points, creating a point cloud model accurate to within millimeters. Photogrammetry builds similar models from thousands of overlapping photographs. These digital twins capture every crack, every subtle curvature, every tool mark, creating a permanent, perfect record and revealing imperfections that are themselves clues. A column might appear straight to the eye, but the scan shows a deliberate, calculated bulge, Entasis confirmed by data. With this perfect model, Engineers then apply finite element analysis, a mathematical method that divides the structure into a mesh of tiny, simple elements. The computer simulates forces, gravity, wind, seismic waves, calculating how stress flows through each virtual stone. This is how we validate ancient intuition. Japanese researchers modeled a traditional pagoda's unique joinery and subjected it to simulated earthquake forces. The dynamic analysis showed exactly how the suspended central pillar and flexible joints create a damping effect, scientifically confirming the seismic wisdom encoded in the timber. One profound application is muon tomography. By measuring the flux of cosmic ray muons, particles that pass through matter, scientists can essentially X-ray large structures. This technique recently revealed a previously unknown void, a potential hidden chamber deep within the Great Pyramid of Giza, showing that even our most scanned wonder still holds secrets. Similarly, detailed analysis of tool marks on stone blocks, using three-dimensional microscopy, can reconstruct the exact sequence and methods of quarrying and shaping, telling us not just what they built, but how they thought as they built it. The Giza Plateau Mapping Project uses ground-penetrating radar and other remote sensing to map subterranean anomalies, tracing the lost infrastructure, the ramps, the worker settlements, and the quarries that fed the construction, revealing the monumental logistics as a landscape itself. Perhaps the most elegant validation comes from the Parthenon. Finite element analysis of its column design demonstrates a breathtaking optimization. The columns are not uniform cylinders, they have a subtle Entasis and a slight inward lean. The FEA models prove this design is not merely aesthetic, it perfectly manages both the constant static load of the marble entablature and the dynamic, lateral forces of an earthquake. The slight lean and bulge actually reduce peak stress concentrations, making the colonnade more resilient. The computer confirms that the builders achieved a near-perfect balance of form and function through geometry alone. So what secrets are we still uncovering with this modern lens? We are finding that their margins of error were often smaller than our own, that their material choices were more sophisticated than we assumed, and that their understanding of force and form was profoundly empirical and correct. This reverse engineering does not diminish their achievement, it elevates it. We are not discovering primitive methods, we are decoding an alternative and deeply intelligent path to resilience. This scientific dialogue with the past does more than solve historical mysteries, it offers inspiration for our future. In an age seeking sustainable design, their lessons in passive stability, material efficiency, and harmony with environmental forces are more relevant than ever. They built for millennia with stone and intuition, we build for decades with steel and simulation. Their legacy is written in enduring stone, and our modern mathematics is now the key to reading it, leaving us to wonder what lessons we will choose to carve into our own age. That single, perfectly placed stone holds another kind of weight. Beyond its geometric precision lies the imprint of a human hand, a life spent in service to a vision far greater than any individual. This is the ethical geometry of monumentality, a shadow calculus of labor, power, and sacrifice that runs parallel to the mathematics of form. To understand these indestructible designs fully, we must also understand the social machinery that brought them into being, the complex equation that balanced stone with soul. For generations, the popular imagination saw these works built by masses of slaves, driven by the lash. Modern archaeology paints a far more nuanced human picture. At Giza, just south of the Great Pyramid, excavations led by Egyptologist Zahi Hawass uncovered the lost town of the pyramid builders. This was not a slave camp, but a structured community with bakeries, breweries, hospitals, and even worker cemeteries where individuals were buried with respect, some with the tools of their trade. Hawass noted that these finds show us the pyramid builders were not slaves, they were Egyptians, and they were proud to work for the king. This was a rotational labor force, likely drawn from villages across the country during the Nile's inundation when farming was impossible. They were skilled artisans, masons, carpenters, and overseers, organized into crews with names like the Friends of Khufu or the Drunkards of Menkora, finding identity and even camaraderie in their shared monumental task. The administrative system behind this was a breathtaking feat of social mathematics. Coordinating thousands of workers required a bureaucracy as precise as the architecture itself. Scribes kept meticulous records on papyrus and pottery shards, accounting for daily bread and beer rations, tool distributions, and work gang outputs. The state had to solve a continuous logistical equation, moving grain from royal estates, fish from the delta, and pottery from workshops to this single, remote site, year after year for decades. This was early state formation in action, the monument acting as a catalyst that centralized authority, standardized measurement, and created complex systems of taxation and redistribution just to keep the project alive. The pyramid did not just symbolize the king's power, it was the very engine that created and demonstrated that power, transforming a collection of villages into a coordinated, hierarchical nation. This dynamic is visible on a staggering scale with the Great Wall of China. Its construction was not a single project, but a centuries-long endeavor that ebbed and flowed with dynastic ambition. The logistical planning was monumental in itself, requiring the movement of millions of tons of stone, brick, and rammed earth across some of Asia's most formidable terrain. Soldiers, peasants, and convicts formed the labor force, their lives directed by an imperial calculus that weighed territorial security against immense human hardship. The wall was the ultimate expression of centralized control, a physical line that defined the state's reach and demanded the loyalty and labor of countless individuals to maintain it. Its indestructible design served an explicit ideological purpose, to project an image of eternal, unbreachable power, both to external enemies and to the subjects within. This brings us to a necessary, reflective question. Does the pursuit of architectural immortality, by its very nature, become intertwined with the concentration of power? The evidence suggests that to marshal the resources, labor, and sustained focus required for such projects, a society must organize itself hierarchically. The vision of a single divine king or a priestly elite becomes the driving force, the mathematical constant around which all other variables, including human lives, are arranged. The monument becomes a tool of social cohesion and control, a permanent reminder of where authority resides, yet to see only oppression is to miss a profound part of the story. For the skilled mason who signed his block deep inside the pyramid, or the soldier who maintained his section of the wall, this work could also be a source of identity, pride, and participation in a grand collective legacy that transcended any single lifetime. The indestructible design, therefore, stands at the intersection of two profound calculations. One is the mathematical mastery of material and force, a triumph of human intellect over nature's chaos. The other is the social equation of collective effort, a testament to human organization, endurance, and the complex motivations that can drive us to build for the ages. To acknowledge this duality is not to diminish the achievement, but to deepen our understanding of it. These stones remember not only the mind of the geometer, but also the hands of the builder, the rhythm of the community, and the weight of the civilization that lifted them, piece by perfect piece, toward the sky. The honeycomb's hexagonal grid is a masterclass in material efficiency, a pattern where every wall serves two chambers and no space is wasted. This is nature's own structural mathematics, an equation for strength written in wax and instinct. We have now come full circle, from the intuitive geometry of the pyramids to the conscious rediscovery of these same principles through the lens of modern science. This is the 13th application, biomimicry, where we are finally learning to speak the ancient builders' language with a new vocabulary of algorithms and advanced materials. We are moving from observing sacred patterns to actively reverse engineering the genius of the natural world, seeking to build our own future monuments that are not just strong, but alive with intelligent design. The ancient fascination with the golden ratio in seashells and the fractal branching of trees was an early form of biomimicry, a recognition that nature's forms solve problems of load, growth, and resilience. Today, we have the tools to quantify that wisdom. Architects like Santiago Calatrava explicitly draw inspiration from skeletal and botanical forms, creating structures where the line between rib cage and roof, between spine and spire, beautifully blurs. His work demonstrates that the most efficient path for force often mirrors the path of life itself. This process is now supercharged by computational design. Parametric modeling and topology optimization use algorithms to simulate forces, iteratively removing material from a digital block where it is not needed, leaving behind an organic, bone-like web that follows precise stress paths. It is a digital form finding that echoes the millennia-long process of natural selection, achieving maximum strength with minimum weight. We see this philosophy manifest in iconic modern structures. Buckminster Fuller's geodesic dome is a direct descendant of ancient triangulation, a spherical lattice of incredible strength born from the mathematics of tensegrity. The Beijing National Stadium, the bird's nest, is a fractal masterpiece in steel, its seemingly random weave actually a highly calculated network that distributes seismic and wind loads across its entire form, much like the interlocking branches of a tree canopy. Marine biologists and engineers are now 3D printing artificial reef structures with complex, porous geometries modeled directly on coral, designed to dissipate wave energy and encourage ecological growth, building resilience into the very coastline. Perhaps the most profound bridge between past and future is the Sagrada Familia in Barcelona. Antoni Gaudí, though working a century ago, was a visionary biomimeticist. He studied forests to design his columns, which branch like trees to support the canopy of the nave. To calculate the complex curves of his vaults, he used inverted hanging chain models, letting gravity itself plot the ideal compressive form. Today, architects completing his legacy use computer modeling to realize his visions of hyperbolic paraboloids and intricate fractal facades, employing stone and modern concrete with the same goal: to make stone seem to grow from the ground. The project is a living dialogue between Gothic aspiration and algorithmic precision. The final frontier lies in the material itself. Scientists are developing self-healing concrete, embedded with bacteria or microcapsules that seal cracks, mimicking the body's ability to repair itself. Carbon fiber composites allow us to create shapes of once impossible lightness and strength, weaving resilience into the very fibers of a structure. This is the next step in the quest for indestructibility, moving from static, resistant forms to dynamic, adaptive, and even regenerative systems. So are we, with our supercomputers and nanomaterials, finally catching up to the intuitive genius of the master builders. In a sense, we are completing a conversation they began. They look to the cosmos and the natural world for their blueprints, embedding timeless principles into stone. We are now using our technology to decode those principles explicitly, to translate the whispers of the honeycomb and the bone into a new language of creation. The question for our future monuments is no longer just how long they will stand, but how wisely they will learn from the world that holds them up. The silent, enduring pyramids and the swaying pagodas are not just relics, they are conversations. Across this journey, we have listened in on the mathematical mind of the ancient builder, a mind that saw numbers in stones, geometry in the stars, and equations in eternity. The true monument, we have discovered, was never just the physical structure of limestone or timber. It was the invisible, immutable framework of principles that conceived it. Sacred ratios like phi gave their forms a timeless harmony. The rigid truth of the triangle gave them unshakable strength. Celestial alignments turned them into stone calendars, forever in dialogue with the cosmos. And a profound, intuitive dialogue with nature, from the seismic dance of a pagoda to the fractal echo of a temple tower, made them resilient partners with time itself. These builders did not fight against the laws of the universe. They became fluent in them, encoding those very laws into their work to achieve a form of calculated immortality. Today, as we reverse engineer their genius with laser scans and finite element analysis, we are not uncovering primitive secrets. We are having a long-awaited conversation with masters. Their greatest lesson emerges not from any single technique, but from the synthesis. True durability, the kind that spans millennia, lies in harmony. It is the harmony between ambitious form and resilient function, between the solid earth and the celestial sky, between precise calculation and boundless vision. They teach us that to build something meant to last forever, you must first listen to the world. So this leaves us, here in our own age of soaring glass and algorithmic design, with a compelling question. What indestructible designs will our era create, now that we are armed with both their ancient wisdom and our unprecedented technology? Will we build monuments that are not just physically permanent, but ecologically and ethically harmonious as well? The blueprint for immortality, it seems, was written in the universal language of mathematics all along, waiting for any civilization with the patience and the vision to read it. We would love to hear which ancient mathematical mystery fascinates you most. Was it the celestial encoding of the pyramids, the seismic intuition of the pagodas, or the silent perfection of mortarless masonry? Share your thoughts in the comments below. If this exploration of monumental minds resonated with you, subscribe for more journeys into the hidden equations of history. The story of how we build forever is still being written, one calculated stone at a time.